In this video today, we will talk about limit laws. Da-da-da-da-da. Well, these are simple arithmetic rules of how to deal with limits. And you find out that we can do almost anything with limits what we can do with numbers. So the first two simple limits are the limit of a constant, c, as x goes to a, is actually equal to c. So if this x does not show up in an expression, then it means the expression is constant in x, and so the limit is the same value as before. Another function we often encounter is x. So limit x to a, x is equal to a. Right? X is a straight line, and we can take the limits wherever we want, and we get this number a. Now here are the arithmetic rules for limits. So we have the limit of the sum, f plus g, is the limit of f plus the limit of g, and the same for minus. The limit of f times g is the limit of f times the limit of g, as you would expect. Now if you build quotients, then you need to be careful that you do not divide by 0. Never divide by 0. Okay, but then you can do limit as x goes to a, f divided by g is limit of f divided by limit of g. And then for exponents like the square root or the square or the cube or the cubic root, whatever. So the limit of the f to the r is equal to limit of f to the r. All these calculations only make sense if the limits exist. So we should write provided the limits exist, right? So here are a few examples to try out these limit rules. So for example, limit x to 3, 2x squared minus 5x plus 3. So maybe first we use the rule for differences and for sums. So then this is limit as x goes to 3 of 2x squared minus limit x goes to 3 of 5x plus limit x goes to 3 of 3. Alright, now for the first function 2x squared, if the limit x goes to 3, we can just substitute x is equal to 3. So we get 2 times 3 squared, which is 2 times 9, which is 18. In the next limit, we get 5 times 3, which is 15. And then lastly, the limit of a constant is the constant itself. So then together this is 6. In general, polynomials like here are very easy to do. You can just substitute the value, and there's nothing to be worried about. Now here's a more interesting example. So we look at the limit as x goes to 0 of root of 2 minus x squared minus root of 2 plus x squared divided by x squared. If in your mind you substitute x is equal to 0, then in the numerator you get root 2 minus root 2 is 0. And in the denominator you get also 0. Okay, so this is of the form 0 divided by 0. And this is always a little bit hairy, right? So we cannot just divide by 0. So what we do instead is a trick which is called rationalization. It sometimes works and it sometimes doesn't. So in this example it does work, and I'll show you how it goes. Let's remove the 0 over 0, because I need space for my little trick. The trick is to multiply with the conjugate term, and this is called rationalization. So what I do is I take the plus term of the numerator, c, like follows. So first of all, I multiply and I divide by the same term, but I use a term in particular to be able to use this formula a minus b times a plus b is a squared minus b squared. So then you see I get rid of the square roots because then I'm able to square. However, I pay a price in the denominator because I have this complicated expression in the denominator now. Anyways, let's try out what happens. So then we get limit x goes to 0. The square of 2 minus x squared, which is 2 minus x squared, minus the square of the other term, which is 2 plus x squared. And in the denominator, we keep the x squared from the front, and then we have this additional factor, root of 2 minus x squared plus root of 2 plus x squared. So let's see what happens in the numerator. This is limit as x goes to 0. So the 2's cancel, 2 minus 2 is 0. And then we have minus x squared minus another x squared. So we have minus 2 x squared divided by x squared times this long thing. And now in the next step, the x squared factors cancel. And we continue. Limit as x goes to 0, minus 2 divided by the root 2 minus x squared plus the root 2 plus x squared. Okay, so does this look better than before? It still looks rather complicated. But now we can try to sub in x is equal to 0. Right, if you do this in the denominator, you get root 2 here and root 2 there with a plus sign in between, so they don't cancel. You get 2 times root 2 in the denominator. So indeed, we can now take the limit. That is cool. So we get minus 2 divided by 2 root 2, which then is minus 1 over root 2. So see, by multiplying with this complicated expression, we actually simplify quite a bit, and in the end we are able to compute the limit, although first it looked like the case 0 over 0, but 0 over 0 is not well defined. It can actually lead to any number, to really any number. In this case it is minus 1 over root 2. Final example, limit x to 4 of 3 divided by x minus 4. If you substitute x is equal to 4, you get a 0, right? This is of the form 3 divided by 0. So this is also problematic. We could try the same idea of rationalization, but it does not work. And so I show you here what does not work, but I still show it. So let's assume I want to multiply with the conjugate term, so with x plus 4 divided by x plus 4. Let's do that. Then we have limit as x goes to 4. 3 times x is 3x plus 4 is 12. In the denominator, we then get x squared minus 16. Okay, so that's what comes out here. Now in this modified expression, if you let x go to 4, then the denominator is still 0. So this is also still of the form, what is this? This is actually 12 plus 12, this is 24 divided by 0. So it doesn't help. We still have a 0 in the denominator. So unfortunately, this idea, although it is a good idea, does not work. Well, for the right idea, we need to go back what we learned in an earlier video using this epsilon notation. You see, as x approaches 4, then x minus 4 gets very, very small. So we have something like 3 over epsilon. Okay? And now it matters if we come from the left or from the right. Because if we come from the left, then x is less than 4 and it is minus. If we come from the right, then x is bigger than 4 and we have plus. So let's do that. This is of the form 3 divided by minus epsilon. So this will go to minus infinity. Well, this is of the form 3 divided by plus epsilon. So it goes to plus infinity. This limit does not exist because left and right-sided limits do not agree and they are infinity. So it's a really big D and E. Now here are two little theorems which allow us to deal a little bit more with limits. So for example, if you have two functions which agree everywhere except a point A, then you can say the limit as x goes to A, if it exists, is the same. So say you have one function, let's call it f, which looks like this, and you have another function g, which is the same function, but the value is included. So then f is not defined at A, but g is defined at A, but the limits are the same. So also in f, if you come from the left or from the right, you approach the same limit as g would. And then here's another interesting property. So if the function f is always lower than the function g, lower or equal, then the limits will be the same. So the limit as x goes to a of f will always be less or equal the limit as x goes to a g of x. Let me summarize. So here is again the list of the limit laws. Right, so interesting is sum and products and quotients and exponents. You can really do the algebra like you're used to it, provided everything exists. And you don't divide by 0. If you have to divide by 0, you have seen two methods. One is rationalization, or just modifying the function so that you can actually take the limit. And the other is to use this idea of 3 divided by epsilon, or something divided by minus epsilon, which gives you an idea of plus or minus infinity. Hey, there's something going on with Tolo and Gela. Let's have a look. Hey, Tolo, hey, Gela, what are you having there? You got a new cat? Let's have a look. Aw, she is cute. Does she have a name? You call her Epsilon because she's so small. Oh, how cute.